Awesome. Thank you so much, Candace. So yeah, to get started, I'm here with Bartosz, and if you have been in the Spark community for the past like a decade or so, you've probably heard from either myself or from Bartosz or from both of us, because we sometimes do these things together as well. But I wrote more recently the Delta Lake Definitive Guide with a set like a slew of different authors as well. Prior to that, I wrote a book for A Press called it's like I can't even remember the name of it. I'm like something about mission critical streaming systems. That was back in 2022. But I've been an author for a long time, been a mentor at work, and have helped teach a bunch of people at a place called the Hacker Dojo in California. If you've ever been there, it's a great place as well. And just I really love this stuff. So I'm happy to share tips and tricks with everybody today. And so I'm going to kick it over to Bartosz to talk a little bit more about himself as well.
Thank you, Scott. I'm also excited to be here today. And besides writing the blog at waitingforcode.com and publishing the book Data Engineering Design Patterns in April, I'm freelancing. I'm doing data engineering, essentially with Apache Spark, Databricks, and Delta Lake. A bit more and more stream processing as well. So pretty excited to be here, and over to you, Scott, to introduce the content of the webinar.
Awesome. Thank you so much. All right, so today we have essentially like an hour or so of kind of back and forth, and we're gonna do Q&A at the very end of this. But for people who've never used Protobuf before or have not heard like talks where I've talked about how cool Protobuf is in the past, or haven't heard of Buff where I currently work, and we love Protobuf, this would be a kind of Protobuf based beginning of this entire conversation. And so really we're just going to try and show you like how Protobuf can help solve some problems. It's not going to solve every problem. Like there's no kind of like silver bullet for a lot of things, but it can help you solve a lot of problems where like data just kind of changes randomly, out from underneath you. I like to talk about like a no surprises architecture, and Protobuf is very good for that. So that's gonna be part one. Part two, we're gonna be basically just diving into real world streaming application patterns. What do they look like? And a lot of this is gonna be also like teasing some upcoming content that Bartosz can talk a little bit more about as we get to that section. And then in the very end, we're going to kind of start off, like not start off, we're going to end with more of an overview of like where we see kind of streaming systems going, what's up with like the whole zero ETL to open lakehouse formats. Why does that matter for you as like a data engineer, data architect, analyst, any role, whoever you are today out in the audience? There's going to be something for you in this entire presentation. And then at the very end, we're also giving away free books, and that's always good. Stay for the books. Hopefully stay for us as well. All right, so moving into the actual journey. So if you've worked with streaming systems before, or if you've just heard about streaming systems, for me, like I got like, I'm like, I don't know, I got kind of the itch for streaming systems back when I was working at Yahoo. So that's been just about 10 years or so where I've been working primarily with streaming data. But the one thing that all streaming systems have in common, so whether we call it a streaming processing engine, anything else like that, like it's data, right? We're sending data from point to point very quickly. And so if you think about a system that needs to be on 24 hours a day, the actual foundation of your data is really the most important thing that you can solve for. Everything else is essentially just bits and bytes kind of moving around. And so, with that in mind, what is that data format that you're using? And, for the most part, it's going to all be row oriented, structured data. And so we're going to take a look at what like pros and cons of each. And it's going to also be kind of through the lens of like Spark. And so if you're not a big fan of Spark, that's okay. This stuff will be, transferable to anything else that you use as well for your processing engines. So one of the things I like to talk about, like JSON is very good for REST APIs. JSON is not very good without a lot of work for streaming systems. And that's because it's very flexible. If you think about like, mutable types, mutable types are very good because they can mutate, which means they can change. If you're relying on something to always be as it should be, then mutability can also be like, not so great. And so I think about that a lot with JSON. So it's like, if we think about like, one release and we have a store ID, it's created at, et cetera, like the JSON blob example I have on the top, it's like, cool, everything looks good. It's very easy to have a release where everything then looks bad. There's ways of handling, kind of mutability and schema changes on the fly, but also there's ways of just having your data be corrupt. So like in the example that I'm showing right now, like there'd be a specific point in time where we had version 1, we have a change, we have version 2. If I want to read back in time for everything from version 1, I wouldn't be able to with the same schema as I would for version 2, and that would make me sad as like a streaming data engineer. And so like I don't want those surprises because I want to be able to essentially write an application, test that application, and then let that loose in the world so that it can just kind of continue to run. And everybody else who's excited about that app being out in the real world will also be happy that it's continuing to run as expected versus not having a status because that's a corrupt field at this point. Um, if you're using Spark and you're using any kind of permissive pass through, a situation like this would essentially just nullify the status field, whether it's nested or non, it would just say status null. And that's not great. So mutability is a blessing and a curse. That flexibility is very good until it's not. And so if you think about that, okay, we have JSON. JSON's very flexible. Then we have Avro. Like Avro's been around, it feels like since like the beginning of time, at least like my time. And there's pros and cons for Avro as well. It's a very lightweight format. It's being used in a lot of places. It doesn't necessarily encode its own schema, and that can also be problematic as well. So you essentially just have a byte buffer. So if you're used to having like nested types and you change the inner nested type, then you can get these array index out of bounds exceptions. And so just like with everything else, right? Best practices are there for a reason, and they can actually help you, to not run into problems, with data in flight. But sometimes, the stresses of the job and everything else cause problems to occur. We talked a little bit about permissive mode before, like in Spark. If I take a look on the right, I'll see like, oh, we've now got permissive mode for Avro as well. Like, not all data is corrupt. Like, I don't want to come out here and, fly some flag where it's like everything's bad. I don't want to be that like a doomsayer. Um, a lot of times though, when things start to go bad, you'll start to notice that that's, kind of like a more like insidious problem that gets worse and worse over time. But permissive mode can help you actually get through those corrupt records to be able to see what the data should be, to go fix those problems that you have with your upstream systems. And so that's Avro. We've talked about JSON as well. I work at Buff, so I usually talk about Protobuf as well. So what is Protobuf? For those who don't really know what Protobuf is, what is and why is Protobuf what it is? Like Protobuf, if you think about it as a message, I've got a message that's a store. I've got an enumeration. I've got an ID. I've got a created at timestamp. I can open my store. I can close a store. The store has a status. Is it under construction? Like all the things that people would have to think about to kind of encapsulate what a general store is. Well, it feels a little bit like JSON because I've got braces and things like that. It's not JSON, and it can be compiled down. And for every single version that's been compiled, I can guarantee that nothing's going to change out from there's going to be no surprises for that version. There's also a lot of constraints and things written into the actual underlying protocol that allows me to safely upgrade my protobuf definitions. So we can talk about these as schemas because we're talking a little bit more about data. This would be no different than like a DDL for normal, like, OLTP database or anything else like that. Like there's specific concerns that I need to think about before making a change that could potentially break a downstream system. Or if I'm the upstream system, I can break everything, right? So the worst places to break everything is completely upstream. And so Protobuf has a lot of stuff built into it. But, what does it actually kind of look like too, right? Like Protobuf works really well with JSON. So it's kind of weird to be like, oh, don't use JSON, use Protobuf instead. But it's interesting that you can kind of have like these interoperability layers so that, systems that already understand JSON can still use Protobuf. And it's pretty flexible to kind of go back and forth between them. But the big thing is that like your data definitions are actually all like encoded in a very type safe format. And so you don't really have to think about like, the type of problems that could occur with JSON. And you also don't have to worry about making kind of breaking changes in general. And so we'll get into breaking changes in just a sec as well. But like Protobuf, like it just feels like a smarter JSON, like in the way that I look at it. And it's also providing those guardrails for your schemas. And the last thing too is that like instead of having to write boilerplate code to produce records in your language of choice, there's code generation. So you essentially create a message and you can compile that down. Buff has a free tool, and if you download our CLI, you can call buff generate. You can generate your protobuf without having to think too much about it, which is nice. But with all that said, protobuf also has its faults. So if you don't think about breaking change detection, if you're changing types kind of wildly, it's going to change what we call like the wire format. And so like the second the wire format changes, we essentially have a corrupt record. So like our bytes are no longer representing what they should represent. So on the right-hand side, I have an example of like what this would look like to use Protobuf within, it's like coffee orders. So if you think about like an order flow or any kind of e-commerce flow itself, if I want to, deserialize Protobuf, I can with Spark very easily just using the from Protobuf SQL function. And then from that, I essentially just get like a data frame row that's then, I can use like I would any other data frame, which is kind of cool. But the one thing that's kind of like a word of caution is that if things do break, I'm going to get these end of wire exceptions. And while I can while I can be like permissive about that, more often than not, if I'm changing something that breaks across the board, I'd rather use fail fast. And so if I'm in Spark and I want to use fail fast because I want to always know that something broke and it's corrupt, you can do this in like your staging environments to make sure that nothing bad ever makes it into production. And that's always a good thing too. So you can never let down your downstreams if they never know that you broke something because it never makes it to production, which is always wonderful. So we've talked a little bit about the shape of the data. We've talked about JSON. We've talked about Avro. We've also talked about Protobuf. And a lot of that is talking about really like the shape of the data that we are sending. What does that look like, right? But a lot of like those data quality problems, as I talked about before, like occur with surprise changes to an expected schema. But that's just essentially like the type safety, the name of our columns, our fields, et cetera. But what about like the actual data quality, right? Like what about like the actual, data contained within fields? Or if we want to think about this as like the data contained inside columns of a row, then what can we do with that? So if I want to be able to fix problems before they occur with the shape of the data, there's something called buff breaking. If you want to hit the QR code, you can. We're going to have this video up on YouTube later as well. You could always go there as well afterwards or take a look at like the buff docs. But we have something in like our free buff CLI called buff breaking. So if you think about schema like conformance and schema like governance and a lot of the fun things people talk about with like the open lakehouse, we have the same thing for the protobuf itself. So if I'm going from one version to another, I want to make sure I'm not going to surprise somebody with a breaking change, then everything can be essentially built directly into our tool chain. So before anything actually gets deployed, it can break the build if we broke our actual protocol. So not breaking protobuf is good because it doesn't break our downstream systems. So it works so you don't have to, which is always great. So that's just for the shape of the data. I don't want to break essentially my container that carries data. But if a container is carrying something that somebody wants, they hope that it shows up. So we don't want like a Titanic type situation. We don't want to sink the ship. We want our data to go from point A to point B and be, exactly what people expected it to be. And for that, we have something called Protovalidate. And so Protovalidate is essentially adding annotations to your protobuf definitions that allow you to essentially have like rules and constraints. And those constraints don't just have to be, they don't have to be simple in general. Constraints can actually encapsulate multiple fields at the same time as well. And so if I click over here, we're just taking a look at the store example, trying to keep it, light and airy for this webinar, but I have my basic protobuf, which still works. It's great. I've got the shape of the data all under control. Then on the right-hand side, I've essentially annotated it with different rules of, it's like, these are my rules of working for this data. And we don't have to go into like exactly what the rules mean, but I think the big and like more kind of interesting thing is that like, it's no longer just a string for my store ID, right? If I take a look down at like row 45 on the right-hand side, string store ID is taking a look at, needing to actually pass a valid UUID. And so some problems creep up and you might expect a UUID, but you get something completely different. You might expect a date, but instead you're getting a string that's not a date. And so being able to check that essentially like right at the edge before data propagates into your actual, data ecosystem is something that's very, very helpful, very useful. And that's something that a lot of times we really think about like in the data engine, like we don't think about as much in the data engineering world. Like we're used to a lot of like cleansing patterns and everything after something is landed. But after the data is landed, if it's already corrupt, there's nothing we can really do about that. So it's much easier for us to be able to test that, are things, solid prior to actually going anywhere where someone actually has to look at it, right? In the same way that we would, test APIs, we would test the requests and responses for them. we should be doing exactly the same thing as well for our data. And so if you want to give Protovalidate a try, we've got a playground. It's just protovalidate.com. It's free to use. You can essentially write Protobuf and then test validation rules against it. And it comes pre-populated with some information that makes it easy to kind of get started as well. And so that's something that we're pretty proud of. And we've even kind of coined a phrase for this, like within like our own ecosystem, where we talk about this as like our semantic validation layer. And so if we have semantic properties of our data and we want to validate that our data is semantically correct, then we can do that before data actually, is written anywhere. So before it actually, lands in like an Iceberg table or a Delta Lake table or anywhere else like that. So why does this matter, Protobuf and Protovalidate? One of the things that like I've been talking about a little bit is that Protobuf itself is essentially kind of, it's like the enforcing rule of the shape of the data. So it cares about like the nesting and how that works. It cares about those inner types, also cares about the types of all of my individual fields, but it really couldn't care what data sent along within those individual fields. And so then Protovalidate comes into the equation because it's then saying, oh, I get it. Like I can go ahead and do the work to make sure that the fields are all correct and that this is following the rules that you've set up. And so we can now do that all in the same place, compile it all down together. And then at that, at the point of build, anytime, where we actually want to test everything, we can do that. So if I want to test this, in, an integration test, I can do that before anything actually hits the wild and goes into production, which is really nice. And so I always talk about this really as like data bliss. It's like, you go from having data quality problems and data quality woes to essentially having data quality as a service that's all essentially encoded in a way that people can reuse it. And so if we want to bubble that up into like the, kind of further into like the conversation that we're having today, we can take a look at these like ingestion patterns. And so in the world of like gRPC and Connect RPC, which is something that Buff is open source through the CNCF, we essentially have many ways of like, emitting Protobuf and creating entire data ecosystems just using Protobuf. So kind of going back to the Protobuf first, notion. If I have Protobuf messages, and those are encapsulating the data that I expect to send to a downstream consumer through a Kafka topic, then I can use everything that I showed today, and we can do essentially client-side validation using Protovalidate. At the very end of the session today, we're going to also take a look at what broker-side validation looks like. And that's something that's kind of more of like an advanced feature that is not available everywhere within the Kafka ecosystem at this point in time. But we'll talk about that later. And so what I've covered right now is essentially we have data, we want to emit data. We'll do that through SDK to essentially like a gateway service that checks and says, okay, is this record valid? If it's valid, that's awesome. Let's send it. It's nice and clean. This is great. We can now use this to make really good downstream data sets, solve all of our data problems. If it's not great, then it's going to go to a dead letter topic, and then we can go figure out what went wrong with that later. But with that said, starting with the topic and moving into data ingestion land with Spark and Flink, I'm going to kick this over to Bartosz. So without further ado, here we go.
Yes, thank you, Scott. Protobuf is very important if you want to set up some kind of solid backbone to your data, but what really matters is what you do with your records, with your events. So to present a little bit what we can do, we decided to discuss sessions that are pretty easy to picture for data engineers, but also for normal users who are not really into engineering, because we all participating in some kind of sessions. Whenever we watch something on streaming platforms, we initiate view sessions. Whenever we are doing the workout at gym, we also have some gym workout sessions when we start exercise and we end the exercise. And finally, we also may have some learning sessions when, like during this webinar, when we start with some little knowledge about the topic, and in the end, we hopefully get better and better, and we understand this given theme even more. And to summarize the session definition, we could say that is a kind of activity followed by a closing action. So like in your gym workout, for instance, whenever you leave the gym, it's the closing action for your gym session. Or you can also close the session with some kind of arbitrary and business-defined period of inactivity, because whenever you can imagine you're watching a movie or a series and you fall asleep, then you are kind of stop emitting the watching events, and the streaming system behind should may assume that after some period of not receiving any action from your end, your session, your streaming session will be, your review session will be closed. So these are just general concepts, but they are involved into data engineering pretty closely, and they are challenging too, because to build a session, you never get the full picture at once. You always get some incremental data that you need to build, compose together, and you need to compose them with some kind of state requirements. So you need to keep the data in flight so that at the closing event, you build and you return the final version of a given activity. Another challenge are unaligned windows. So window processing can sound easy in data engineering because it's always limited to some start and end time with potentially some kind of sliding in between. But for sessions, you cannot have aligned windows like in more general data engineering terms, simply because, for example, when you take the gym example, you will not have all people coming to the gym at the same time. So they will be a little bit much more distributed, and there may be sometime the gym will be crowded, and another times it will be more free. So you will need to deal with that part too, and it impacts the reprocessing. That will be another point in the list. But before that, we also have the late and disordered data that can make the challenge for idempotency for the session ID generation, because you may assume that when you base your session ID generation on the event time, and you sometime in the future you get late data, so you may have to integrate this late data and generate consistent key. Otherwise, idempotency may be broken. It can also be problematic in terms of reprocessing. So you can see that it all boils down to that it's not only because at least processing is also a little bit involved in this late and disordered data problem. When you have at least processing, I mean that your job may retry, or even you can run an explicit backfill action to fix some bugs in the code. So for that reason, it's very important to respect the semantics and to handle late and disordered data properly. Otherwise, you can introduce some mess in the generated sessions. Code regressions and reprocessing are challenging too, because when you take the example of aligned windows, you can simply define time boundaries and reprocess the code. So fetch the data from a lakehouse table, delta lake table, iceberg table, and ingest it to your job and reprocess, generate the aligned sessions. For the unaligned sessions is not the case, because even though you have some time boundary, you can have the session that starts in the adjacent partitions or in the adjacent time boundaries, which make the whole code logic for the reprocessing more challenging to write. And finally, there are job updates and state preservation. State preservation is like can be also a bit bottleneck for smooth updates. It can take time before your job fully checkpoints all the in-flight states and lets you update the application. So it's also one of the challenges involved with session generations and with stateful processing in general. But hopefully, even though they are challenges, we can turn them into opportunities and try to define some kind of generic solutions that could apply across various technologies and business domains. And for that reason, I call these kind of things in the book design patterns. And regarding the book, there are two versions currently. Thanks to Buff, you can download it for free from the first QR code. And if you prefer the hard copy, you can always go to Amazon and get your own version. And quite important thing to know is that there will be an extra chapter in the digital version added probably somewhere in January. But it doesn't mean you have to wait to January to download the copy. You can download it right now, and you will be notified by Buff about this new chapter available. But let's go to the business. If I can say that, the pipeline we are going to analyze today is composed of a lakehouse table, like Delta Lake table, and a broker, which is an Apache Kafka compatible technology. And in the middle, we have our data processing job that will be responsible for generating the sessions and writing them continuously to another Apache Kafka compatible topic. And to address few challenges from the list, we are going to use hybrid source pattern and also stateful sessionizer. They are not all the patterns that you could use here, to be honest, but let's stay within time and focus on these two that are pretty important to do it properly and clearly from the day one. Regarding the hybrid source, the problem is that when you build your session logic, you can opt for two strategies. You can either start from scratch and use the real-time data, which is often limited to maybe some several days, like 7 or 14. Or you can also combine your historical data that sits in a cheaper storage for longer period of time with this real-time data. And that's what the hybrid source does. It kind of includes all that happened before you started thinking about sessions into the pipeline you are going to develop. And it's pretty important because it gives you some kind of past information you could use to better control the present and the future. You could, for example, use the sessions from last Black Friday to know how your users behave, adapt some kind of, I don't know, maybe promotional offer, or adapt the navigation on your e-commerce store. So it can be important also from the business standpoint, even though it sounds also challenging from the engineering part. It sounds challenging, but there is kind of template or design pattern that solves this issue. And it generally decomposes the problem into two parts. The historical one that you can see in the top of your screen, where we are explicitly fetching data from the past year, and the real-time part, so the current data in the bottom, where we are fetching data from particular offsets that is not present in the table. And to schematize a little bit this picture, we can say that hybrid source implementation splits into three steps. The first one consists on identifying all the sources that needs to be involved in the implementation. In this step, you also need to define the boundaries for these sources so that the data will not interleave with each other. Later, you of course run the sources one by one, and in the end, you need to switch to a real-time pipeline. And there are two possible solutions. Either you use the framework-based solutions that is natively provided in your data processing library, or you can also leverage data orchestrator and define much more logic in the code, but you will see that it also gives much more flexibility. For the first solution, the framework-based one, in the screen you can see an example of hybrid source API in Apache Flink, where we start reading some files before using real-time data in Kafka for building the real-time sessions. And here on purpose, I omitted the boundaries for the file source because we can also consider that this file and source, but more general, the historical source will not receive any data in the future. In that case, you can just take it as is and process everything before switching into the real time. And the real time, as you can see, I use this set starting offsets to clearly identify the timestamp where the real-time processing should start. And this approach, even though it looks simple, it has some gotchas. Like it's not supported everywhere, so it's a kind of high-level API that depends on the framework you use. There is no such a kind of easy way to define hybrid source in Spark, unfortunately, at this moment. And the second and much more serious probably issue is that your streaming source will be also subject to this, will be executed on the same infrastructure. So typically historical data is much bigger than real-time data, and in that case, you might need some much more powerful cluster to handle the load and not wait too long. And that's what the hybrid source in data orchestration does. So typically, it separates the historical data processing from the real-time data processing and let you configure the infrastructure as you wish. The problem is that you need to code the synchronization logic. You need to probably have two different jobs, and you need to also pass the state between these two jobs. That can be quite challenging, even though there are APIs to read states in Flink and Spark. So it's doable, but it requires some coding effort compared to the hybrid source approach in the data processing frameworks presented previously. So that was for the hybrid source. Now it's stateful sessionizer. The idea here is to use a component that will give us safety in terms of deployment and in terms of fault tolerance, meaning that we will not be worried about deploying a new version of application because maybe you might be worried because if your state is volatile, of course, when you deploy it, you will lose it. So that's what this stateful sessionizer tries to address. Generally, it's a kind of persistence that you add on top of your processing logic that generates these sessions. And under the hood, it's, as I said, it's an additional component that is added to the job, and it interacts with your business logic. And there are two approaches again to implement it. Either use the framework based or use the custom. And the custom is pretty rare because it involves writing a lot of code that is already provided in two popular data processing frameworks for streaming, which is Flink and Structured Streaming. And so generally the steps can be summarized to these three parts. So you implement your business logic with this intermediary state management in mind. So that means that you don't consider you have all the data to create the final session at the moment, that you can open it, for instance, in the next execution. Later, you configure how your state store should look like. Currently, you can use in-memory structures of your programming language, like hash maps in Java, or you can use a dedicated state store mechanism like RocksDB. And finally, you need also to leverage your data processing framework to call up adequate method to update the state in the state store. So it's mostly the API interaction between your business logic and the framework. And how does it look like in real example, or not full example, but that's the general idea. With the transform with state transformation added in Apache Spark 4.0, where you define your business logic like a stateful processor function. You define your output structure to the downstream consumer so that you can control the types. It's very important if you followed Scott's explanation about Protobuf and type safety. And you also need to define how you will expire the state. So you can use the processing time, or you can use event time that follows the data semantics that you are processing. And when we take a look at the stateful processing function, it has three main API methods: the init, where you initialize the state, so you define everything you need here. Later, you have the handle input rows, where each time whenever you get a new row, you kind of extend the lifetime of the session. And you can optionally also return a partial view of the session at this moment to your downstream customers. And finally, there is the handle expired timer, which is called once the session really expires. So either it reaches the processing time timer, or your real-time data moved enough that you can consider you will not get any new data for the particular session. Yeah. So it looks simple because you generally need to just learn the API, but it has some implications on runtime. The state store gives you safety in terms of deployment, in terms of fault tolerance, but it's also a kind of blocker because whenever you add a new worker or you need to scale your processing, you need also to scale this state accordingly. So you need to distribute it in the way that there is no two workers processing the same state instance. So it can add a little bit more overhead than simply adding a machines and waiting for the load to distribute. Then another part is related to the latency. So state store will save your state into some resilient storage like object storage that have quite big SLA. And it of course adds some IO and network traffic that can penalize the latency. To overcome that, data processing frameworks use either explicit checkpoints when you explicitly call a CLI met command to perform the checkpoint, for example, before deployment, or some irregular asynchronous checkpoints that do not block the whole execution, but that are performed at some interval, meaning that during this interval, you can have some data to reprocess in case of restart because it wasn't saved to the state store yet. And finally, there is a kind of business implication, the late data. Even though you use the event time semantic and you may be considering the session you emit with the handle expired timer as complete from this standpoint, there is still risk that you receive some kind of event lost in the wild that came after a few days and that your session is not 100% valid from the business from the business perspective. But again, it's not easy to solve because you will need to open the session, rebuild everything, and probably store this intermediary format for much longer. And it is quite challenging. It not yet that well supported in this framework-based solution. But as regard how does it relate to Protobuf? So even though the code and logic doesn't really touch Protobuf, except the write and input, Protobuf simplifies a lot because it reduces the network footprint, so you can send more data, which is pretty convenient if you use cloud services that have limited throughput, like for example, like Konieczny data streams, when you can write 1 MB per second, if I'm not mistaken. Protovalidate brings this semantic validation that gives you much more confidence for the data you are delivering. And of the second one is the metadata and all things related to the schemas, so that you don't need to worry about schema evolution in the code. It's much more simpler to express with the metadata. There are some cons I saw is like this serialization, the serialization overhead in mind that you know that your data is not string, so you cannot simply take it and read in your, for example, debugging sessions or in the tooling. Whenever you prepare your data for testing, you will always need to build these binary formats. So it's a little bit a small overhead, but for me it's like in the number of process cons, you can see that Protobuf is much more pro than Con, in fact. So it's just to be aware of a few things. But yeah, I hope that Scott convinced you that he's a great addition to the any data engineering stack. And regarding other patterns, so today we discussed only the hybrid source and stateful sessionizer, but there are a few more present in the book that you could also use to solve the sessionization problem. Keyed idempotency to mitigate the add list processing and late data risk, and streaming late data detector to detect late data and eventually run a kind of secondary backfill pipeline to fill in the gaps, and streaming reprocessor to reprocess the data whenever it's still available in your real-time broker, and partial state writer to inform your customers how this session generation advances. And these two, streaming preprocessor and partial state writer, will be present in the new PDF that will be available on the Buff site website, probably in January. So regarding Buff, Scott, do you have something more to share?
I'm glad you asked that. Yes, yes. Thank you, Bartosz, for going through like the patterns. And just to wrap up as well, a lot of like the patterns that like we've looked at today are ways of handling data in flight and then eventually doing something with that. So if we think about like any kind of data engineering, right, where I'm looking at static table to static table, that's all good. But when I'm taking a look at like data that's essentially like unbounded, that is also kind of volatile because some of the unbounded data is being deleted over time, for cost savings, et cetera. There's pros and cons to when things go wrong. And so one of the things that like I'm going to talk about today that is like a it's a technological like innovation from Buff, is what we call buff stream. And so if you think about Kafka compatible APIs, there's like 10 or feels like 10 or 20 in the market right now. Um, Really like the differentiator that we have like for buff stream itself is that all of like the validation logic is not pushed down to the producing client to be able to say like I'm sending data that I know is correct. They're going to send data and that's great, but the broker that's essentially part of like the quorum for an individual topic is going to actually be the one who's saying yes or no for whether or not data should actually be allowed to go downstream, either as a traditional table or to be archived into an actual Iceberg table itself. And so with BuffStream, you have essentially the ability to, you know, have a kind of exactly once processing to Iceberg, which is neat. It gets rid of that whole entire series of problems of having to actually, ingest from Kafka through a streaming job just to write to, one of your lakehouse tables. But it's also, it kind of gives you, the best of both worlds as well, depending on if you want to be, kind of a true, streaming first company, or if you want to just get rid of like the problems of, how do we reliably get our data into the lakehouse? And so with that, if you want to find out more about Buff Stream, you can just take a look at it on like our Buff website, or reach out on like the Buff Slack as well. And so with that said, we're going to switch over to Q&A mode, and get some things like get some questions answered from the community as well. And so before kind of getting started on like the canned questions, there was one last thing that we talked about in the webinar like overview that we didn't really get to during the presentation, and that was essentially like how do you choose, what's the correct lakehouse format to choose. And I think like I don't know, Bartosz, if you want to pick up on this one as well, give your 2 cents. Like you've worked across like pretty much every single lakehouse format. I've done the same. We can have a little conversation about that as well. There's no wrong answers, right? So if you want to give me your 2 cents, that'd be wonderful.
For streaming, you mean I really like the change data feed, the possibility to streamline all the changes you made on the table without having to write any custom incremental logic like between timestamp filters or anything like that, just to get the info how your table and how your data evolved. So that for that reason, I really like the working with Delta Lake for all these kind of real-time use cases. But other than that, I think that I don't see any huge difference in terms of user experience and engineering experience as well.
I would have to kind of agree with that too. Like there's no real like I think nowadays like there's no kind of like one clear winner for everything. Like a lot of it's kind of just like marketing in general. Use what works, right? Like if something works best for a specific use case, use that. Everything else is interoperable, right? For the most part, everything is actually being written to Parquet. And really the only thing that changes is like, manifest lists and, the way that we actually, describe files in a snapshot. But aside from that, like it's still your data, and you can still guarantee that that data is not going to just randomly disappear and become corrupt, as long as you follow the best practices of those individual, lakehouse formats. So to answer the question that we had posed before, like use what works. And right now, until V4 of like the Iceberg specification, you're not going to have as easy of a time doing kind of pure streaming applications using Iceberg as end to end your streaming format for that. But that's changing. I think like a lot more of the market is moving towards streaming first, and or there's a component of streaming that's going to be in every enterprise across the world. And so just knowing that everything will eventually probably feel the same anyways is always a good thing to know. Um, Okay, so on to the next questions. There's a question that's saying essentially integrating Protobuf to CI/CD workflow. It's like, what's the overhead of including the necessary tools for generating the classes? And so I can pick up this one. So it's not necessarily like a lot of like additional overhead. It really depends. Like if I have Protobuf, Protobuf is language agnostic. So it's not like, oh, like only write in Java, etc. You have essentially like a compiler that will compile your Protobuf definitions for your language of choice. So say that's Kotlin, say it's Swift, say it's, I don't know, Python, Rust, etc. The overhead would essentially just be generating those packages or those libraries to be able to bring into your APIs or into your data workflows itself. And so there's not a ton of overhead for that. There's also something called the buff action. So there's a free open source tool that's been, I'm like, oh yeah, it's been open source. That's in the name of it as well, but it's called buff action, and it is just a Git workflow that you can add to do all of this into your CI/CD workflows as well. Okay. So if you think about so this one I'm going to give to Bartosz. So it's like, how do I get started with the hybrid source pattern in Spark?
It depends on how do you want to implement it, or what kind of approach. You can kind of simulate this with the framework based in the single pass by generating the sessions, writing to some intermediary store and reading them back. For example, with as an initial state and the transform with state, or you can also use this data orchestrator approach where again you need to save the state somewhere and use the initial state parameter of the transform with state transformation to load this state as a bootstrap to your stateful logic. So that's kind of internal details, but for me, what is the most important is to clearly identify the boundaries so that you really know that the data you are processing will not be interleaved or that will not be empty spaces or anything, any kind of issues you may face that will not be saved, I think, with Protovalidate this time, because when you have some gap in the data, you cannot really consider it as a row level issue. It's more like chunk data issue.
Yeah, I would agree with that too. I think for a lot of stuff, like I think a lot of the new tooling has made it a little bit easier to get to the specific, like say it's in Kafka, getting to the specific offsets to be able to take a look at say you have 64 partitions and then you have 64 different offsets for your starting offsets. It's easier to be able to encode that. Like with Spark, you've got starting offsets, you've also got ending offsets that helps you clearly define like the boundaries of an individual batch. And then even like in stream, like if you think about like Delta, for example, I've got like starting version or starting timestamp. We'll take a look through the transactional log and take a look at, what was the transaction closest to an individual timestamp that's been given, or the explicit actual transaction identifier for that. The same thing is true in like Iceberg, where you actually have individual snapshots. As long as you haven't cleaned up the table and gotten rid of those old snapshots, then you can get back to that specific point in time, and then that makes those filling those gaps a lot easier. As long as you have the data, I think that's the big part, right? The data is gone, it's gone. Hopefully, there's a way to get back to it. If there's not, there's other problems to be had that would be a whole nother session on debugging and regenerating data that's been lost. But it's good times. These are problems that everybody who's ever been a data engineer has had to suffer through before. If worse comes to worse, just write your data, ahead. So if you think about, taking it off of Kafka and writing it directly to, Iceberg or Delta, gives you a safe spot to basically pick back up from. In other sessions, like one that Bartosz and I did about a week ago, we talked about that as like the tin pattern, or like the eventual extractor pattern, where it gives you a safe place to go back to. And then let's see. So time wise, we got some time for some additional questions as well. Let's see. So there's one where it's like, so how to integrate Protobuf while debugging a streaming job. Debugging a streaming job is not easy. And this is like all part of the same question. So debugging a streaming job is not easy, but if you add a binary layer on top of it, it looks even harder. Like any tips, tricks to understand how to, get these messages in flight. Bartosz, you want to pick that one up, or do you want me to take it?
You are the proto expert, so I leave you the floor.
Well, thank you. I think with everything, right? Like, so say I have, say I have JSON data that's coming out, coming down like off the, out of like Kafka or anything else like that. It's still going to be encoded, right? It'll be like base 64 encoded, so that we're sending back, we're sending binary data. It's just being done behind the scenes. And so there's going to be, some work regardless of taking, data that we have we are either going to infer the schema of, or we know the schema of in advance, to be able to kind of step through and see if it looks the way that it should look. With Protobuf, the only difference is that we're essentially using a descriptor set, that's going to generate a struct like on like the Spark side, or we're going to be creating like a special like special survey like on like the Flink side as well to be able to handle that Protobuf. Um, there's also like there's stuff that I think it's probably more kind of advanced level, but like there's something called Protoscope, that came out of Google, like came out of the Google company that people know about. And Protoscope will allow you to take a look at like even like corrupt protobuf messages to be able to understand what like the intention of that data was. But hopefully, like if you're using like the buff tooling, you're using like buff breaking, you're not going to have to worry too much about like corrupt data. But we're all human; these things happen, and there's tools to help you kind of get around those. And so, for a lot of things too, like if you're a company starting off on this journey, the tooling really is like the first place to get started, right? Making sure that everybody is comfortable with that tooling. Anybody who's on call is comfortable with being able to, spin up, a notebook, go fetch some data, take a look at it, figure out what went wrong with it, and then slowly work back up so that the pager can get resolved and everything else like that. But with everything, it's going to be there's a learning curve, and then once the learning curve's over, hopefully things are a lot easier than they were before. So the big thing is that you have a solid schema for your data in flight, and then you have a very solid schema also for the data once it's actually at rest, if you're using like a lakehouse format as well. Um, and yeah, so we've got a few more minutes left. We're running out of questions. Bob, is there anything else you want to send through as well? Or Candace, are there any other questions that have come through? If we have time to answer that, we will.
Yeah, there are a few more questions in the Q&A. I don't know if you want to pull that up and look through there, or do you want me to read some out?
Hold on. So I'm gonna just pull them up to my screen. Okay. So the question from Paul Trepka, asking about, it's like, seems like a cluster is going to need additional resources. How are they limited to, how are we limited to charge additional money? What's the cost optimization? Not sure. Not sure what that's what that was essentially asking about. But if it's essentially like about like these types of like solving like these kinds of problems, like cluster resources, like if you're talking about running like say like in Databricks or somewhere else like that, like you can go serverless for a lot of this. Like I think like if you think about like the overhead of running like these different jobs, like it all depends on time. And so if there's a specific like time to get a job completed, then you can put more money at that. If you don't have necessarily like a time boundary, then the job can basically run a little bit slower. One of the things I like to talk about a lot, like in the Spark world, is like using trigger available now. And so if you're running essentially like stateful micro batches, in the same way that you would like batch jobs, that can be a really good way of like reducing like your overhead to still run jobs that are stateful without having to worry about like setting up really complicated batch jobs themselves. And like I go back to Nike use cases. Like we used to be able to handle around 5 million events a second on about it was a 2 node cluster that had was that it was a M7 uh 2XL like GD. So it was like the it was like the Graviton processors with like a direct disk. And so you can do a lot with a little, just depends on like the way that the data, like the shape of the data, the complexity of the job itself. So hopefully that was hopefully that was good for that one. Um, and then let's see. So we also have There's another question where it is, does Protobuf solve the schema evolution? And so this will be the last question, so we wrap up on time. But so does Protobuf solve the schema evolution problem? We need a schema registry so that the schemas can be shared between various parts of the application. Otherwise, each is going to maintain their own version, and that's going to be a mess. So is that still going to be there? Bartosz, do you want me to answer this one as well?
Schema registry is a kind of source of truth for all the schemas, so there is no risk that one team will pick up a proto definition and adapt it to their own needs, breaking everything. So yeah, I think this is a kind of important component
Yeah.
to make it work.
I would agree with that too. So like if you think about like data discoverability, like a lot of times like the schema registries are just there to discover, other like other data definitions, like within, an enterprise, for example. A lot of times if you are a smaller company and, say you have a team of 10 people, a lot of times you can keep a lot of that information like pretty much like in your heads or in like GitHub. At a certain point in time, like feel like you're reaching like a tipping point where things are starting to kind of feel like they're getting out of control, then schema registries are a lot better at being able to give you a place to be able to go and unify like your documentation for what your data definitions are, to showcase any like the rules and rules of engagement, etc. Like Protovalidate, for example. And like shameless plug, Buff has its own schema registry, which is very good for Protobuf as well, and that allows you to unify like your APIs, allows you to unify like your analytical pipelines, all within like a single pane of glass. And with that, I'm going to pass this back to Candace and the Linux Foundation, and thank you everybody else for showing up today and asking questions.
Thank you so much, Scott and Bartosz, for your time today, and thank you everyone for joining us. As a reminder, this recording will be on the Linux Foundation's YouTube page later today. We hope you join us for future webinars. Have a wonderful day.
Bye, everyone.